And we're screen share. Good. Okay, back to the beginning.
All right. Can you hear me? So now I'd like to start the talk today. Okay. Sorry. My talk is this title, and let me start from this figure. The nickel copper multilayer thin film developed by Iwamura and Ito, they are my colleagues, of course, is an important seed to develop clear energy, as mentioned by Dr. Iwamura on the first day of this session. Here, I just show this structure again. We have a ceramic heater and both samples on the two samples on the ceramic heater, and we put the sample in the vacuum. Excess heat measurement cycle is something like this. First, we have to, in the absorption of hydrogen stage, pressurized with this 200 to 300 Pascal and temperature like this. And then after the time, 15 hours, we quickly evacuate the system. Simultaneously, we heat up the system. And then system goes to the desorption time, where the hydrogen gas is coming from the film, and then make an excess heat. We are measuring this time. The good features of this method is when its excess heat source is in vacuum, and temperature range is rather high, and of course easy to handle thin films instead of the powders and something like that. And also many possibility of radiation measurement. But difficulty in reliability calorimetry, because we just until now mainly only the temperature measurement, and I feel it is not sufficient. So I just to show you why the temperature measurement only is not sufficient. So this is the heat flow model, a very simple model for this structure. We have a heater inside the sample, and we have a sample on the surface. So we have a two heat source. One is heater from heater, and another heat flow is coming at the surface, from the surface. If the excess heat generation occurred, the heat flow is coming this side. My question is, we are usually using the calibration by just changing this temperature, the heat flow from the heater. Is it enough? So I just calculate, it's a very simple calculation though. Here you have a delta P to the input power. And temperature of core is changed, of course, by just this period. Is it same as the temperature change if the excess heat coming from the other side? The answer is no. The delta T in core temperature caused by delta P in does not match delta P in PEX over here. The calibration of TC by changing P in usually underestimate excess power. The another problem we are thinking is just a change of emissivity of the material. So I changed the emissivity changed and do the calculation again. The result is this red line. Of course, if the red line is corresponding to the emissivity 80% of the blue line, then the result is this curve. It's always overestimated. So temperature of core strongly depends on emissivity of the sample. Decrease of emissivity due to, for example, hydrogen gas overestimate the excess power. Of course, measurement of radiation itself gives more reliable excess heat. So now, this is our experimental setup to measure the whole, wide range of photons from, let's say, 0.22 to 5 electron volt. We put the 3 detectors, one optical to ultraviolet region over here, and 2 near-infrared region. This is also the spectrometer, Fourier transform infrared spectrometer over here. And the another one is the mid-infrared region. This is just a radiation thermometer though. So combined to these 3 measurements, we can get a very nice spectrum in wide range in energy. Okay, how to calibrate those respective measurement? We use the carbon nanotube. This is a very nice tube because the radiation from the carbon nanotube is known just as a black body radiation. We can calculate the black body radiation using this formula and plot this. For example, 800K. Then your output of, let's say, from a thermometer is this. You just normalize this. And for this region, also you can normalize that. Then we can get a calibrated spectrum. So this is the result of a calibrated spectrum of carbon nanotube. Black and green and blue and red. These are the different temperatures. And you can get the
今天晚上那个会议主持人都是用美国的。为什么今天晚上的主持人都是美国的？有一个是他早上4点半的。
I'm sorry, I cannot hear you. Something wrong?
Continue on, Hiro.
Okay. So this is the data again checked by fitting the using this function, and you can get the temperature from here. The real temperature is this, and the obtained temperature is this, almost within the 1 or 2 degree difference. That's very nice. What I want to stress here, you can have a raw data, but the spectrum obtained calibrated in this way, you can get a spectrum in absolute intensity. So you know how much photons coming from you're observing. And this is a correction for almost all differences, like absorption and solid angle difference and so on. Samples we tested. 2 types of metal samples were examined. So nickel copper multilayer foil, 6 layers of copper and nickel, and also pure nickel foil. So let's see the result. So this is the result of our nickel copper multilayer. 2 spectra for the different input, heater input power. You see the blue spectrum and the red spectrum. Red one is, of course, with hydrogen, red H2. And the blue one is without. You see the increase of intensity, whole regions, including the very low energy region. And if you increase the heater input, the similar, but a little bit more intense for this region. So what I want to say, the spectrum from nickel copper multilayer is very nice. Gray body approximation is used, okay, in this formula. So therefore, we can deduce the emissivity and the temperature very precisely from the analysis of this spectrum. And this is just a general, if you compare with hydrogen to without hydrogen, usually temperature increases 4 to 7%, but emissivity decreases 10 to 20% for this sample case. So this is not negligible, but we are very safe. Even if this decrease, we know that the radiation power is increased because this is just a direct measurement of this one. Yeah, you see, from here, we are visible light region. So I'm saying this is a direct visual evidence for the excess heat generation. Yes, you can see the red light shines 2.5 times brighter. If you have a very nice eye, you can really saw the effect of this so-called anomalous excess heat generation effect. Okay, we need
3 minutes, Hiro.
No, thank you. We need a model to extract a quantitative evaluation. Evaluation will be quantitatively, because not only the radiation from sample, we have a radiation from the holders. So therefore, we just put a simple model again to sample surface and from a holder surface over here, and then various equations over here. But what I want to stress is the radiation from sample B and the radiation from sample A. These are measured, and we use we need a effective temperature over here. To do that, we use the temperature core and the temperature measured over here. These are the measured values. Then we can get a calibrated line. So this is the calibrated line, just one parameter finally, alpha. We put the alpha, for example, 0.76, and then the total power, total output is just calibrated by this calibration run. And then you apply this equation for the measurement, you can get the excess heat in this way. So this is the excess heat spectrum, excess heat versus input power. You can observe the excess heat to 60 watt. The excess heat increases as input increases. So, but these excess heat variation is just depend on the elapsed time of experiment. If you put the various data in this way, you know this is just going down. It's as if the decay decay of the reaction rate for like this. The simple interpretation is the number of hydrogen in the sample decreases, then the reaction rate decreases. But you continue to the, let's say, for example, to 120 hours, about 5 days, then there's still excess heat over here. So we think this is just a 2 decay component. And we can apply the 2 decay component like this. Then we can integrate all this region. Finally, we can get a produced energy in 120 hours, like this order, about 700 kilojoule. This corresponds to the about 4 keV per proton. Okay, so temperature dependence of excess heat is something like this. We have if temperature goes up, you can have excess heat goes up. We put the three graphs or three lines over here. This is a simple fit to the data, just linear fit. From here, if you have a threshold for temperature, the temperature is something like this. But we know that very low temperature, we have also the excess heat, so this cannot be applied. And many people applied this one as just a so-called Arrhenius equation used in chemistry. Then we apply that. That is the blue line. So the activation energy is something like 0.6 electron volt. But in nuclear physics, we are always using quantum penetration like this formula. So apply this one. This is just red line over here. Then we can get the so-called gamma energy is 14.9 electron volt. Because, yeah, we need a more wider energy region to check this kind of tendency, which is the best to explain. For example, if you enter this one, the Arrhenius fit and the quantum penetration fit is changed like that. Okay, since I don't have any time, I just say the result. So this is a radiation spectrum from nickel base itself. It is obvious that there's no difference. The hydrogen gas, this little effects on pure nickel foil. The excess heat from the combined foil, I mean, nickel copper based on nickel foil must be due to nickel copper multiplied layer part. And then finally, what about the difference between the H2 and D2? Just glance at the latest spectrum. We have 3 detect spectra over here. One black is calibrated spectra, red with D2, blue with H2. So the result shows no essential difference between H2 and D2. It's a little bit difficult to understand because the Q values of a reaction, elemental reactions are very much different. And also the reaction rate for the elemental reaction is very much different. But this is the first glance of preliminary data. We need to repeat more measurement, of course. Now, summary. We have performed radiant calorimetry by combining 3 photon detectors for study of anomalous excess heat production from nickel copper thin foil with hydrogen gas. The intensity spectrum in wide energy range provides visible and clear evidence for the anomalous excess heat. The value of the anomalous excess heat can be obtained more reliably by incorporating the radiant intensity into the heat flow model. The nickel copper multilayer foil with hydrogen gas produces thermal power of about 2 to 6 watts, but the pure nickel film did not. Just for the one sample though, the excess power lasted for a long time after the absorption hydrogen gas once. total produced energy in 120 hours was about 720 kilojoule plus minus 220. The reaction rate declined over time. This may represent a decrease in the number of hydrogen participating in the reaction. The excess heat generation is temperature dependent. The higher the temperature, the larger the excess heat. Potential barrier for the reaction to start. The preliminary data indicate that the amount of excess heat with D2 gas may be similar as with H2 gas. Okay, thank you for your attention. So this is a collaboration, and this work supported by Clean Planet. Thank you.
Thank you, Hiro. We are 5 minutes past the break start, but you got yours in 20 minutes. So I'm going to ask that you either email questions to Professor Kasagi or to get a hold of him even during the break if you have a chance, and also during the discussion time.
Okay.
We're running a few minutes late, so I'm going to declare a 10-minute break, returning at 15 minutes past the hour.
Okay.
Thank you, Francis,
yeah,
for sharing. I think people can get the discussion right now if you wish.
Oh yeah.
Okay. Yeah, we have a hand. Yes. Luciano, are you unmuted?
Okay, thank you, Professor Kasagi, for your work and for your presentation. And what do you think is the reactions, the nuclear reactions that are happening in the nanolayers? That could be nickel plus hydrogen, copper hydrogen. What do you think that is happening there?
Well, I am not quite sure what kind of reaction, what kind of nuclear reaction is happening there, because we spent for time to look for the gamma rays from not this experiment but the other experiment. I was involved in the NEDO experiment also. There we measure the gamma rays with a nickel plus hydrogen system and no gamma rays at all. Using the high resolution gamma germanium detectors, we can easily distinguish if some of the reaction occurs. We should see some gamma from the remnant of that, but we couldn't see anything about that. So we rejected the gamma ray energy region, and then we also look for some of the high energy, let's say X-ray, and for example to see the bremsstrahlung gamma rays, but we couldn't see anything either, and so on. Now, I just for a while we are just looking at this this photon energy region. You see, so therefore, right now, I have no idea what kind of reactions occur. Okay, is that okay?
Okay, thank you. Have you made any evaluation of isotopic composition or elemental composition on the nanolayers after the generation of heat?
Well, we are just right now. We are just now concentrating on photon detection. Maybe if after we get a very nice mass spectrometer, Q mass or so, very expensive one, we will do that. But of course, the Hamamatsu and Itosan also doing the other using in the other experiment, just check the Q mass measurement, but that's it. Okay.
Okay, thank you.
Okay, I don't see any other hands. I guess everybody wants to do their break.
Okay, thank you. Thank you, Fran.
Thank you, Hiro.
So you said I have to start 15, 11, 10, 15?
Yes, 10:15 China time
Okay,
or
So-
Xiamen time.
yeah. Yeah. You can,
All
you
right.
can take a rest.
For your information,